Hello everyone, my name is Gretchen McCarthy. I'm a current PhD student here at the University of Otago, and I study the ecological interactions between bivalves, which are creatures like mussels and oysters and clams, and large brown macroalgae like kelps, but also large fucoid species like Durvilia or bull kelps. A little bit about me and my voice probably, and also this lovely sweatshirt. You might notice that I am originally from North America in the United States. I did my undergraduate degree at Boston University with a focus in biogeochemistry and oysters. So that was the beginning of the academic journey that I've begun with bivalves. Journey with bivalves began actually as an oyster farmer, which was kind of the job that everyone got in high school back in my hometown. Which is quite a good first job. I recommend it. But through that, I really got an eye into the production of bivalves and aquaculture systems. But also by doing that, I kind of saw there were a lot of gaps, particularly in the knowledge of science being conveyed to farmers, because science communication is sometimes something some of us scientists lack on. And that's really what drove me in my undergrad to be a biogeochemist who focused on oysters, and specifically how oysters had the effect to influence biogeochemical processes within estuaries. Largely, I looked at nutrient cycling, so how does the behavior of this little guy living in estuaries affected bigger processes? But I was still just working with one species in monocultures, so that really drove me to come to the University of Otago here in New Zealand because I wanted to understand polytrophic interactions. So that's what's led me here to focus on our green-lipped mussels and their interactions with large brown macroalgae. So polytrophic, it is a little bit of an intimidating term, but it basically means poly, meaning many, and trophic, referring to trophic level. So some of our creatures are first producers, are lowest in trophic levels, but then they're consumed by things like grazers, which would be a first trophic level, and those grazers are consumed by predators, which could be you and I, which in that little simple food web, we would be the second trophic level. So a big part of my PhD is looking at food web dynamics between these two counterpart species, and one way to do that is with isotopes. Isotopes are these really cool things in atoms that when you get differences in the amount of neutrons and protons, you can get heavy and light isotopes. So for carbon, usually carbon is carbon-12, but I look at carbon-13, and there's also that nasty twin carbon-14, which is radioactive, which I thankfully don't work with. But by understanding the differences in the ratio of carbon-12 and 13 that naturally occur in the systems that I study, I can trace those differences through trophic levels to see how organic matter goes from plants into animals and then eventually into us. So I use isotopes in some of my PhD work to understand how material travels through food webs. And a big aspect that affects some of this work is we are changing the amount of carbon in our systems through the production of fossil fuels. So something that I sometimes have to look at is how this changing baseline in carbon dioxide, especially entering marine systems, affects the different ratios of food webs. So as people have been burning fossil fuels, which is carbon that has been stored in the earth for a long time, we're actually changing the natural ratio of that carbon-12 and carbon-13 that we see in the atmosphere. So in order to address this, scientists like myself who use carbon as one of these isotopic tracers in food webs sometimes have to correct for this value. And we do this by looking back over time, and sometimes air bubbles that are in Arctic sea ice or Antarctic sea ice down here, to see how this variation in the natural abundance of carbon-13 in the atmosphere has changed over recent decades. And this is really important because if we want to understand how carbon moves through food webs, we need an accurate representation of how we as people are changing it through the burning of fossil fuels. Carbon dioxide is a really important gas that you guys have learned about in this system. It's a greenhouse gas, so it makes our planet nice and toasty by helping retain some of the sun's energy. But unfortunately, it does have some negative caveats, especially as you guys have learned, it's being absorbed into our oceans, and creatures like bivalves, which I look at, use calcium carbonate to build their shells. So when we actually get a more acidic ocean, sometimes these shells are compromised and they become thinner or more fragile. And this is especially something in industries like Cawthron, which are looking at the artificial production of bivalves through the rearing of spat, which are little baby bivalves, where this pH can actually be a huge issue when these baby bivalves are first building their shells. And this is because they're little, they're quite fragile, and if the water becomes too acidic, they could literally dissolve away, which means that some of our Kaimoana species could be quite threatened in the future if this ocean acidification is left unchecked, but also misunderstood. There is the potential in the fields that some people are looking at producing genetic strains of bivalves that might be more resilient to differences in pH and also temperature, because these things kind of go hand in hand. But it is really important that we understand this changing in ocean pH to protect these species for future generations.